So this video we're going to talk about the variable oxidation state of transition elements. So in the previous videos we have discussed the characteristics of transition elements. First, they can form colored iron, but actually it's not all of them. Remember, scandium iron and also zinc iron, they are colorless. Okay. Next, they will form variable oxidation state in their compound. This video we're going to talk about that one. So the last character, that will be can have a catalytic properties. Before we look at the transition metals, first of all, pay attention to the elements from the main group. You realize that mainly for the elements from the main group, they can only form one type of ions. For example, lithium, they will form lithium ion Li+, beryllium Be2+, They seldom form more than one ion. However, in transition metals, you will find that they have a lot of ions. Ti can have like +2, +3, +4. Manganese, can from +1 all the way to +7. Maybe they are not forming a simple ion, but they can form compounds in different oxidation states. But you have to realize that scandium and also zinc is also the special one. They can only form one stable ions. So for the rest of them, you can find that they can form more than one oxidation state. But among different oxidation state, some of the oxidation state is stabler than the others. So the one highlighted in blue, it indicate that those oxidation state for that particular elements, it will be stabler than the others. So why do they have variable oxidation state? The real reason actually is too complicated for you. But we'll just simplify them. You can have a look of the scandium, titanium, and vanadium. Right now, you can see that the electronic arrangement is 2892 or 28112. So actually this one, we can express in another way. Think about argon. Argon actually is 288, is that right? So we can use this symbol, bracket argon, to represent this part. So after that, say scandium, is 2892, So on top of that, actually you have 3 more electrons. So they will arrange like this way. You have 3 argon electronic configuration and has 3 extra electrons. So when they form ion, actually where are the electrons coming from? The electron is coming from the outermost shell. This is the outermost shell. And then they will have next inner shell. So in total, you can see that they can remove up to 3 electrons in this case. For example, the one in vanadium, you'll find that the outermost shell, you got 2 electrons. And then next inner shell, you got 3 electrons. So at most, there are 5 electrons right there. So you can find that, if they have 5 electrons, they can remove one by one, and then they can form +2, +3, +4, and +5. So that would be like that. But actually, it is not that simple because you still have other concepts like half filled, full fill, and things like that. But basically, you can see that the electrons can remove from the outermost shell and also next inner shell. This one, it is 4. This one is 3. So this one, we call this one outermost shell. And then this one, we call that next inner shell. So what you need to explain, in DSE level is just this one. You just tell them that, because variable electrons, that means can be 2, can be 3, those electrons can be removed from the outermost shell and also the next inner shell of the transition metal. So therefore, they can form ions, or compounds with variable oxidation state. So this one is a key statement for this chapter. So how oxidation state affect its chemical property? So you can see from this table, take for example manganese +7, actually it is the compound of permanganate. So permanganate is having oxidation state +7. So for this one, because it has the highest oxidation state, it have rooms to go down from +7 to +2. So therefore in this case, you can find that MnO4- can act as a oxidizing agent. So for ions in high oxidation state, they have room to going down, so they can act as oxidizing agent. For example, MnO4 minus, for example, Fe3 plus. While the other one, okay, you can find that, okay, if we have like low oxidation state, for example, Fe2 plus. So in this case, okay, it can then go up, okay, become Fe3 plus. So this one, if the ions with low oxidation state actually have rooms to going up, so they can act as a reducing agent. Okay, so this one from +2 to +3, ON is increasing, so therefore it's having a oxidation process. So Fe2 plus can act as a reducing agent. So based on the oxidation state, okay, this chemical can act as either oxidizing agent or reducing agent. Let's have a look of some examples. So first of all, for the ion, okay, they can turn from Fe2 plus to Fe3 plus. We know that, okay, Fe3 plus is more stable than the Fe2 plus. Why do you know that? Okay, you can think of the rust. Hydrated iron 3 oxide. Remember the terms? Hydrated iron 3 oxide. So if you leave the iron there, okay, untouched, okay, it will finally turn into iron 3 iron instead of iron 2 iron. So between Fe2 plus and Fe3 plus, we say that they can interconvert to each other. Okay, so in case 1, you can find that iron 2 iron. We have iron 2 iron right here. Okay, they add as a Ra from +2 to +3, they have an oxidation. So when the Fe2 plus mix with chlorine, okay, the greenish yellow, okay, greenish yellow solution. So chlorine from 0 to -1, okay, it is a reduction, 0 to -1. While this one is +2 to +3. So this one having oxidation, while the other one having reduction. Okay, so in the process, okay, you see that this one is pale green, and maybe greenish yellow, and the product, okay, we got yellow one and also colorless. So you can see the product, okay, it will be in total yellow in color. Okay, so this one iron 2 iron add as a. So in case 2, okay, iron 3 iron, okay, this time we have iron 3 iron, they add as an OA because it is from +3 to +2. Okay, it is a reduction. +3 to +2, okay, it is a reduction, while the other one, okay, in this case we put copper into it, okay, the copper will then become +2, it is an oxidation. So when we drop a copper into Fe3 plus solution, copper will become Cu2 plus, which is blue in color. Okay, this one is blue in color, and then, okay, the Fe3 plus is reduced, okay, to Fe2 plus. So therefore this one, okay, is green in color. So the green plus blue, okay, so you can see the bluish green color right here. So you can see that the oxidation state of the compounds, okay, it will affect its chemical properties. Next, we can have a look of manganese. Okay, for manganese, actually you have a wide range of oxidation state from +2 to +7. So the most common one, we always see that we have Mn2 plus, MnO2, manganese 4 oxide, which is +4, and also we have permanganate, which is +7. Okay, so in case 1, okay, if we are having in acidic media, the permanganate ion can act as a OA, a very common OA, and then reduce to Mn2 plus. So this one, okay, MnO4 minus becomes Mn2 plus. If I add SO2 in it, which is sulfur dioxide, and then turn into sulfate, okay, so in the process you see that, okay, it will drop all the way to Mn2 plus if it is in acidic media. And the color will change from purple, which is colorless, okay, we mix together, they form very, very pale pink. You can hardly see the pink color, okay, because it depends on the concentration. Normally you say colorless will do. In case 2, this time, okay, we put it in alkaline media. Then, okay, the permanganate, instead of going to Mn2 plus, they will go to MnO2, which is brown precipitate. So you can see that in this case, okay, the MnO4 minus is reduced to MnO2, which is brown in color. So you can see that at different media, actually they will give different product. So what you have to memorize is in acidic media, MnO4 minus will become Mn2 plus, while in alkaline media, MnO4 minus will become MnO2. Okay, so how the exercise will look like. Okay, so it will just like this one. Okay, stated oxygen state of iron 2 chloride. Remember, sign first. Okay, plus go first. Most stable oxygen state, okay, we mentioned is +3, and then react with bromine with iron 2. Okay, state the chemical species gave the pale yellow color of the solution. At the end, it turned from pale green to pale yellow. So the pale yellow is go to Fe3+. Okay, and then you have the state and ionic equation. So actually, it's quite typical, okay, for a question like this. But I just want to draw your attention to question number 2. Explain why MnO2, okay, act as either oxidizing agent or reducing agent. So this one, actually, we cover this one in redox reactions, okay. Some of the chemical, it can act as OA and also can act as RA. So you can have a low of MnO2. For this one, actually, the oxygen state is +7. So it can have room to go to +7 and have room to go to +2. So therefore, we can say that, okay, the oxygen state, okay, is +7. So it can be reduced to different oxygen state, and also it can be increased to different oxygen state. So therefore, this one can act as both oxidizing agent or reducing agent. So to summarize this video, first of all, you have to realize that, okay, some of the chemicals in main group, okay, they can only form one type of simple ion, main group one. Okay, while the other ones, okay, in transition metals, we find that, okay, they can form transition metals, they can form variable oxygen state, but not all of them. Okay, scandium and zinc, okay, actually they can only form one ion. Okay. Because the reason for that, okay, you have to remember that is a key for these videos, because they can lose variable number of electrons from outermost shell and next inner shell. Pay attention to the term is next inner shell, not next innermost shell. Okay, so among all these, okay, some of the oxygen state are more stable and common than the others, and if the ion is in high oxygen state, they have room to go down, so therefore they act as an OA, while the other one in low oxygen state, they can go up, so therefore they are normally acting as RA. So different media, they can also affect the product form. Okay, we mentioned before MnO4-, it can either form Mn2+ or MnO2 in different media. Okay, and also some of the ion or compound, if they are having oxygen state in the middle level, like +4, okay, like MnO2, they can act as ON and RA as well. So that's all for this video. Bye bye.